So, good morning. Today in this lecture we are going to discuss ANOVA and, if we have sufficient amount of time, correlations. Well, a couple of weeks ago we learned how to compare sample average with a number, or how to compare two sample averages, or how to compare variances. Well, for sure, pairwise comparison of means or variances is a popular tool in statistics and can tell you a lot about phenomena we study. However, often we need to compare more than two means. For example, you have three shops and you need to compare three average prices of something among these shops. Well, imagine that you have three choices. For example, you are a fresh graduate and you have to make a choice where to work. You can work in industry, you can work in consultancy, you can go to financial sector. Well, and average salaries in each of these sectors. Well, and you want to conduct a simple research to learn whether these salaries are the same or whether these salaries are different in terms of statistics, because you have some sample, you calculated salaries using such a sample. And we use ANOVA to do this. We use ANOVA to compare multiple averages, or we use ANOVA to compare multiple sample averages. Well, itself this topic is large, and definitely it's impossible to discuss all ANOVA tools or the whole ANOVA analysis within short lecture. And today we are going to learn just basics of ANOVA, the most basic and simple tool when we compare multiple means. Well, and next step or another interesting tool is correlations, which is often used in econometrics and in statistics as well. When we use econometrics, imagine that you need to find a relationship between two phenomena. For example, imagine that you have information about returns of mutual funds. Well, and you have a simple question. Well, is it true that investing in a mutual fund is the same as gambling? Well, you can answer to this question using simple correlation coefficients. So, and by the way, the right answer will be true. So just if you randomly choose a mutual fund, it will be the same as gambling. Well, and for sure, we usually use correlations to find relationships, for example, between earnings and spendings, or between consumption of something, of one good, and consumption of another good, and so on. Well, but first let's learn ANOVA, and let's discuss what ANOVA is. And today for sure we have to do a couple of exercises in Stata to learn how to estimate ANOVA analysis. Well, let me start with the theory first, and let's discuss what ANOVA is. Well, full name of ANOVA is Analysis of Variance. Well, ANOVA, and ANOVA. Well, in general, ANOVA is a statistical test, and it works likewise any simple statistical test we know. What does it mean? It means that first step, you have to formulate statistical hypothesis. And as usual, you have to formulate two statistical hypotheses: null hypothesis, alternative hypothesis, and equality operator must be a null hypothesis. Well, Next step, do some calculations. You have to estimate some statistics, and finally you should compare the estimated statistics with its critical value, or you have to rely on p-value approach. Well, and we use this information, so we use p-values or critical values to reject or don't reject the null hypothesis. That's it. Well, and so let's discuss in greater detail each step. First, you have to formulate statistical hypothesis. What here the formulation is easier than that of pairwise comparison of means. Well, you know that when we conduct pairwise comparison, we have to make a decision whether we need to run one tail test or two tail test, whether we are looking just for a simple difference between two averages, or we need to find out whether one average is greater than another, or vice versa. Well, but in ANOVA, usually hypotheses are the same in all exercises. Well, null hypothesis states that all means are the same. So all means are equal to one another. And alternative hypothesis states that not all means are equal, or robustly speaking, it states that there is at least one mean which is different from other means. Well, and in principle, that's it. So you again, when you work with ANOVA, you have such a hypothesis. They are the same in all exercises. What it could be different is the number of means we compare. Here I compare c-means. Well, meaning that because it is a hypothesis in its general form, but we can work with 3 means, 4 means, 5 means, but we cannot work with, no, we can work with 2 means, but it doesn't make sense because in this case, you should rely on t-test. Well, next, okay, we have a statistical hypothesis. That's great. Well, what we can do else? Next, we have a data set. We should open data set and we should define 3 things. First, we have to define the response variable. Response variable is used to calculate our averages. For example, if I want to compare average prices among 3 shops, I have to work with the variable price or something measuring prices. If I want to compare average GPA among student groups, my response variable is all GPAs of students. Well, but it's not sufficient. But we need to do something else in addition to this variable. We have to find a factor. Factor is a quantity under examination in an experiment as a possible cause of variation in the response variable. Simply speaking, factor is a grouping variable. For example, when we conducted t-test in state, we had a group variable, self-employed status or gender, or it was a brand name, for example, in your home task, and so on. Well, factor is a variable name, usually, always, and you have to find a variable which splits your sample into levels. Levels are categories, measurements, or strata of a factor of interest in the current experiments. Or it's also called population. Levels, for example, if our variable is binary and it takes 1 if a person self-employed and 0 if a person paid worker, levels are self-employed and paid worker. For sure, we can work with 3 levels, for example, self-employed, paid worker, and unemployed. Well, and so on. And the third important element you have to consider is whether your design is balanced. Well, design of your experiment is balanced if factor levels have equal sample sizes. What does it mean? It means that, well, levels are, we can say subsamples. For example, our factor is occupation. There are three occupations: self-employment, paid worker, and unemployment. If sample sizes of, so if the sample of self-employed, sample of paid worker, sample of unemployed, so all of the samples are the same, well, we can say that our design is balanced. No, by the way, in practice we rarely work with balanced design. So in most of cases, our design is unbalanced. But if you want to apply ANOVA, you should always find factor, level, and response variable. No, by the way, it's pretty easy and it is clear from the task. Well, no, this is example. So you know that we work with databases. So databases in our case is just a spreadsheet. It's a table. Well, and we can imagine it as a simple Excel spreadsheet. We have number of observations, some observations. So they are our rows, and usually columns are our levels. For example, in Excel. In Stata for sure we can. And in each cell we have some values of our response variable. No, in Excel we can make table like this. In Stata there is no need to create 4 variables. Instead we have one response variable and one factor variable. Well, and once we have one variable defining 4 levels, well, we say that we work with single factor ANOVA or one-way ANOVA. Well, and we have 4 levels. So if we work, for example, with self-employed variable, we have 3 levels. Well, and in this example, by the way, we see that all sample sizes are the same among all of our levels. Hence, we deal with balanced design. Well, okay, let's do a simple exercise. Everyone, please read this text and type in the chat what is a single factor, what are the 4 levels, what is a sample size, and that's it. Read this task and write in the chat answers to these questions. Georgi, could be, but waiting cannot balance your data. It can make your data more representative in practice. Okay, good. Well, and the right answer is, so no, you're right. So factor is customer order value is single factor. So more sales, 4 levels, 4 store locations, so all stores, and sample size, you're absolutely right, is 8. Good. Well, this part is simple. So now if we want, for example, to continue this simple exercise, we can look at the dataset. Dataset can be like this. So by the way, sample is pretty small, and when we run a simple analysis, we should formulate statistical hypothesis. We have 4 levels, hence we have to check whether 4 averages for population means are the same as well, or there is at least one mean which is different from others. Next, if we rely on ANOVA, we should check whether all of our assumptions are satisfied. Well, there are 4 ANOVA assumptions. You have to remember them, and note that we always ask we always ask students to list assumptions behind each statistical tool. What assumptions in ANOVA? First, all populations are normally distributed, meaning that your population data must follow normal distribution. And well, we have in this case actually 4 levels, and within 4 level population data must follow the normal distribution. Next assumption is pretty important. Population variances are equal. Yeah, we know that they are normally distributed. You know that when variances are different, or some distributions could be very narrow, other distributions could be wide. Well, it's easy to imagine. But here we assume that all distributions have the same width, well, meaning that all population variances are equal. And third assumption is also important. The observations are independent. That is, the occurrence of any individual value doesn't affect the probability that any other observation will occur. This assumption could be tricky, because if you have 4 store locations, at a first glance, you can say that they are independent from one another. But imagine that your stores are located near one another. For example, you have 4 stores in the same mall or in the same place. And in this case, their sales could be dependent. How to identify whether observations are independent? The easiest way to read the task carefully and to think whether there is any information that your samples aren't independent. Well, for example, if in our task I state that these stores are located close to one another, you can say that, okay, our sales cannot be independent. Well, and for sure the data are interval or ratio level. As we deal with continuous variables, we cannot apply ANOVA for proportions or other variables. Well, what we have? So we can assume that all populations are normally distributed. We can assume that these variances are the same. Well, that's good. What else? We can assume that, so there is no any information in our task that our stores could be, that sales in our stores could be dependent. Well, hence we can assume that these sales are independent. And for sure, sales is continuous variables. Sales is continuous variable, hence we can apply ANOVA. Well, okay, we see that there is a hypothesis. All of our assumptions can be satisfied, and we can argue why they are satisfied, which is important. And next, we can run the ANOVA itself. Well, what is the logic of ANOVA? Well, first, the idea is following. The null hypothesis that the population means are equal should be rejected if the variation between sample means is large relative to the variation of the data values within the sample. Well, as to run ANOVA test, we have to work with variations. Well, and on the basis of variation comparison, we make a choice between null and alternative hypothesis. And in the first step, we need to calculate different variations. First, we have to calculate sum of squares total. So it is the difference between each value in our data and grand mean. Grand mean is the average of all values for all factors. So for sure, this difference must be squared, and we have to find sum for these differences. Next, we have to find sum of squared between samples. Well, Here we find differences between averages for each factor, for each level, and grand mean, and multiplied by sample size. Well, and finally we estimate sum of squared within samples. And by the way, all of these inputs, SST, SSB, SSV, are related to one another. SSV is the difference between sum of squares total and sum of squares between samples. Well, or we can imagine that sum of square total is a sum of squares within samples and sum of squares between samples. Well, it is first step. We have to calculate three things. Next step, well, we have to calculate mean square between samples, and we have to estimate degrees of freedom. Mean square between sample is easily calculated. You have to use SSB and divide it by k minus 1, where k is number of levels in your analysis. And apply this formula to estimate mean square within samples. When we have these two elements, we can calculate statistics. Well, to calculate statistics, we should divide MSB by MSW, and our output is a value which follows F distribution. And next, we have to apply F statistics tables to make a decision. We have to compare the estimated F statistics with its critical value. Well, and if we draw a picture, the logic looks like this. Well, look, we have to identify 2 degrees of freedom, right? We have 4 factors, 4 shops, 4 store locations, k minus 1, 4 minus 1 is 3, and n is total sample size, so 32 minus 4 is 28. Well, and if we calculate our f is 1.03, well, and we have to compare our estimated f with its critical value. If we see that estimated f is larger than the critical value, we should reject null hypothesis. In my example, it is smaller than the critical value, hence I cannot reject null hypothesis. Well, and that's it. That's it. Well, what is the drawback of ANOVA? Look, in this simple example, we learned that we shouldn't reject null hypothesis, that statistically all average values are the same. Well, but often we have cases when average large values aren't the same. For example, we see that there is at least one average is different from another average, and in this case we could be interested to identify, to compare each mean, to identify where is the largest mean, where is the smallest mean. Well, and to do this, to conduct pairwise comparison of means, we can work with Tukey-Kramer procedure. Well, again, it makes sense to work with Tukey-Kramer procedure if we reject null hypothesis. If you reject null hypothesis, please always apply Tukey-Kramer procedure to find what means can be larger than another means. By the way, Tukey-Kramer procedure isn't a single procedure to run a pairwise comparison of means. There are multiple procedures. Well, but in your textbook, of course, employ this one. Well, how to work with it, I will show you in Stata. Well, okay, Stata exercise. Let me send you data first. Now everyone, please download this dataset and open it in Stata. If you are ready, please press plus. Okay, very good. Very good. All right. Okay, well, now let's do the same exercise in Stata to learn how to conduct ANOVA analysis. As usual, you should start writing log file. Please, let me share my screen. Well, first, start writing log using ANOVA lecture txt replace t. Please start writing log file. That's important. Okay, good. Well, now if we look at our variable list, we see that we have just two variables. We can open the spreadsheet of our data using command browse. Well, look, and in contrast to my screenshots in my lecture slides, we have just two columns. One column is x. X is our response variable, and in total, look here, we have 32. So one column is x, another column is factor variable. Another way to do the same job to look at our spreadsheet is to use command list. Yeah.
Excuse me, we can't see your opening windows.
So I would like to stress list. I'm not sure. Did we learn list command?
Yes.
Yeah, list. So no, you can also make it shorter. Well, and what we have here, look, we have variable factor, we have variable x, and within variable factor we have 4 levels. Well, x is continuous variable, and it could be interesting to make a simple descriptive statistics for x. So we see that, okay, average is 8, 2.7 is standard deviation, minimum and maximum. So there is no something unusual in our descriptive statistics. If we look at the detailed summary statistics, we see that median value and mean values are close to each other. Well, also we see that skewness and kurtosis are close to the benchmark values. Well, and also we could make a short histogram to look with, for example, bins, 10 bins. Wait a little second, please. Yeah, and we can create some histogram for our x variable. Well, we see that definitely, x seems that it doesn't follow normal distribution. Well, it could be a problem for our analysis because our sample size is small, and so it's unclear whether this distribution is normal. But anyway, let's try to use ANOVA. The next step, it is always important and interesting to look at our factor variable. If we look at our factor variable, we see that we have the same samples in each level, 8 cases, 8 observations in each level. Well, and we have 4 levels in our analysis. How to run ANOVA test in Stata. So as usual, there are 2 ways to do this. One way is to use our buttons or panels. Another way is to use command line. Let's do both. If you want to rely on the simplest way, you should go to statistics. Next, you should go to summaries, tables, and test. And no, I think that no, linear models and related. And here it is, you can easily find ANOVA MANOVA. Oh, by the way, we won't learn MANOVA, which itself is pretty interesting. And what we have. Analysis of variance and covariance, test linear hypothesis after ANOVA, specification test after ANOVA, one-way ANOVA, large one-way ANOVA. We should use one-way ANOVA. And the common name is one-way. Well, do you see my window? One-way?
Yes.
Yeah, and now we have to fill this all of empty spaces. First, so I mentioned that when you conduct ANOVA analysis, you have to find the response variable. No, in this case, it is pretty simple. Your response variable is x. Next, you have to, x. And you have to find factor variable, it is factor. And you can click submit. If you click submit, Stata will produce ANOVA table. Well, please do the same. And type plus if you have the same output, we have to interpret it. Okay, very good. Well, and look, in the lecture I mentioned that when we calculate ANOVA, we have to calculate SSV, SSB, SST first. It was our first step. Outputs of the first step can be found in the second column, SS. SST is here. It is SS means sum of squares. Sum of squares between groups is here. SSW is here. Well, and let's check, is it true that sum of these 2 numbers equal total? Well, we can type D 22.0 plus 0.9. Yeah, so indeed, so I didn't take into, so I rounded my numbers, so pretty the same. Well, next column is about degrees of freedom, and as expected, first we have 3 degrees of freedom because we have 4 factors. Well, 4 minus 1 gives 3, and last degrees of freedom is total sample size is 32 minus 4 is 28, and last degrees of freedom is total sample size minus 1. It is 31. Well, and if we divide 22 by 3, we will have this number. Let's check. 22 divided by 3. 7, 3, 3, 3, 3, right? And also we can divide this number by this number. For instance, this one by 28. Again, no, almost the same. And if I divide this number, I will get this number. Okay, we have 2. This is MSB, MSW, likewise in my lecture. Well, and almost last step is to calculate F statistics. To calculate F statistics, I have to divide 7,333 by 1.103. And look, 1.03. Exactly the same number. No, and now, so you know that Stata, likewise any other statistical package, employs p-value approach, and we see that our p-value is larger than any usual alpha, it's larger at least than 0.1. Hence, we cannot reject the null hypothesis. Well, and we can make a conclusion that all means, so all average sales for shops are the same. What else? So fortunately, here we have some interesting options. Bonferroni, Sheffy, CDEC, produce summary table, suppress the ANOVA table, and so on. Let's discuss all of them. We can enable first produce summary table and click submit. What is the difference now? Look, if I produce summary table, if I use option tabulate, Stata will create a table with summary statistics. And by the way, it's pretty convenient for us because it calculates simple descriptive statistics. So this row is the same as the output after some command. And in addition, it calculates averages for each factor. What is average for level 1, for level 2, 3, 4, and their respective standard deviations and sample sizes. It is pretty convenient to look at our averages, and so our preliminary analysis could be, so we can compare them. So we see that, okay, so averages, so especially 4 and 2 are close to each other, well, probably 1 and 3 are different from other variables, but because of small sample, well, we cannot reject null hypothesis. Do this. Okay, hope you did. Next interesting option, and probably, no, for sure you can suppress mean, standard deviations, and number of, what does it mean suppress? You can remove, for example, means from your summary statistics. What I suppressed and Stata published standard deviations only. But to be honest, I rarely suppress something. Well, also we can remove ANOVA table. Or we can, so don't break white tables if our tables are white, or we can show numeric codes. No, if we have some labels. No, usually what you have to use, my recommendation, always produce summary table. Well, also we have 3 interesting options: Bonferroni, Sheffy, CDEC. Why we need all of this option? If you read the heading multiple comparison test, it could be clear that these options are used to identify what averages are very different, so are different from another averages. In this case, by the way, it doesn't make sense to click on these options because we didn't reject null hypothesis. But if you reject null hypothesis and if you need to find the largest mean, the smallest mean, use at least one. For example, if you click Bonferroni, in addition to summary statistics, to analysis of variances, Stata will produce such a matrix. What this matrix is? So 1, 2, 3, 2, 3, 4. These numbers are our levels. Well, and these tables show, and these numbers, which are all numbers, show differences between means. For example, average, the difference between average for level 1 and for level 2 is 2. Let's check. 1 and 2. Difference between 9 and 7 is 2, right? Exactly the same number is here. Difference between 3 and 1. Well, 8 and 7 should be 1, and so on. What, for example, difference between 4 and 2 is small, And indeed, if I look at so it is 4 and 2, so this number minus this number gives such a small output. Well, and here below we have p-values, so whether these differences are statistically significant, and we see that for sure all of these differences aren't unstatistically significant, as expected. For sure, you can add Schiffer or CDEC comparisons, and usually they produce identical results. Well, and in addition to this one, for example, 2, well, when we need to use these tables, we need to use these tables when we reject null hypothesis, and we need to find the largest average or the smallest average. Well, and about question, so also you can use if statement and weights. You can use weights, frequency weights, or analytic weights, but we won't discuss it in this course. Well, what else? What else in state? So if you want to work with command line, you should use command one way. X factor, tabulate, and state will produce exactly the same output. Well, what else? Also, there are some interesting in ANOVA tests. If you go to summaries and classical test of hypothesis, well, so yeah, one probably, yeah, one important note. Please remember that we cannot replace ANOVA with a set of pairwise comparisons, because if we do this, our analysis will be too optimistic. We can identify statistically significant differences where these statistically significant differences don't exist. Well, don't replace them with t-test. And what else? Also in status there is interesting command p-we mean, well, which is used to do pairwise comparison of means, likewise CDEC or Monferroni. For example, pairwise comparison of means for x variable requires the following output. PW mean x over factor. So x is our response variable over factor is over what variable we compare. And look, Stata produces, no, probably this table is more user-friendly because it estimates, this table clearly states what means we compare 2 with 1, 3 with 1, and estimates the difference. And by the way, these differences are the same as differences in Monferroni or CDEC table. In addition, Stata calculates standard error and confidence interval for these differences. Well, and we see that 0 is inside of our confidence interval, hence this difference cannot be statistically significant. And also we can work with method. Here we can define here method. Wait. Yeah. Yeah, Tuki is here, and we can use mCompare option to rely on Tuki method. Well, if you want to check yourself. No, in principle, we see that we have different mean comparison tools like PW mean, Bonferroni. To be honest, they produce similar results, especially if you work with large samples. And in reality, you definitely will work with large samples. Well, that's it about basics of ANOVA. And any questions? Okay, good. So now we have to discuss correlations. So in addition to ANOVA, it's important to learn always correlations. When we need to use correlations, as I mentioned, we need to use correlations when we look for relationships. Well, and first, what we can do when we work with relationships. First, we can create a simple scatter plot. I know that you learned scatter plots in your research seminar course when you have learned Excel. Well, so, and we won't discuss it a lot. And in addition to scatter plots, you can calculate correlation coefficients. What correlation coefficient is? Correlation coefficient is a measure of the strength of the linear relationship between two variables. And note, keyword here is the linear relationship. Well, what does that mean? It means that you can fit a line between two variables to explain the relationship. For sure, the relationship can be non-linear, but we won't discuss it now. Well, and the correlation is a very useful measure because it has a certain range. It ranges from -1 to +1. It cannot exceed minus or +1. Well, and if your correlation coefficient is 1, it means that it is a perfect correlation. For example, a relationship between two the same variables gives perfect correlation always. And zero correlation means that variables aren't related to each other. Well, interpretation is simple. Well, how to calculate it? First, as a beginner, I recommend you to create scatter plots first. Scatter plot can tell you a lot about potential relationship. For example, if your scatter plot looks like this, we can say that relationship is linear and increasing, or it is linear or decreasing. However, relationship can be curvilinear like this. We see that it cannot be a good idea to explain the relationship between y and x using a line. It's better to just to fit a curve in this case or this case. Or if we see that all points looks like a cloud, we can say, it is impossible to identify any clear picture. You can say that there is no relationship like this and this. For sure, this illustration is a serious simplification of the reality, because in the reality, you really have charts like this. Well, next step, if you, for example, if you have a scatter plot like this or like this, you can calculate correlation coefficients. I won't explain this formula in detail because it's better explained in your textbook. I would like to stress the intuition. Well, actually, so you can calculate it, and what you should do, so an output of this formula is a number. It is a single number. Well, this number is between -1 and 1. If you see that correlation coefficient is greater than 0, you should say that a relationship is positive. If you see that correlation is less than 0, is negative, you should say that relationship is negative. And once your correlation coefficient is closer to 1 or -1, you can say that correlation is strong or not strong or very strong. Well, something like this. What example? So if you see that scatter plot looks like a lion, definitely your correlation coefficient will be 1, +1, or -1. Well, when we have correlation coefficient 1, when we want to calculate, when we estimate correlation coefficient between two variables, and these variables are the same, have the same values. Well, but often we need to correlate, we need to find correlations between two different variables. And in this case, we can get a case like this. So it is linear decreasing correlation, and look, the correlation coefficient is -0.55. Well, what does it mean? It means that we have a negative relationship between y and x. Or in this case, we see that correlation coefficient 0.7, it is positive, there is positive relationship between y and x, but looking at scatter plot, we cannot say that we should trust our correlation coefficient a lot because relationship isn't linear. Well, and once we apply to a linear correlation coefficient to explain a nonlinear relationship, our correlation coefficient could show that, so it could underestimate the real relationship. We see that if we apply, if we fit a curve, it could be a good approximation of the relationship. But here, if we apply a line, it cannot be good, well, because of this correlation coefficient is underestimated. And the extreme case is here. We see that the relationship between y and x can be perfectly explained by the parabola, or by the U-shaped curve. But if we calculate a linear correlation coefficient will be 0. Well, it will be a horizontal line. Well, and does it mean that the relationship between y and x doesn't exist? No, it doesn't. Well, the relationship exists and it's pretty strong, but we applied a wrong tool to explain such a relationship. And how to define whether the relationship is linear or nonlinear? So you can learn it from your prior experience, from theory, well, or from the chart. But to be honest, in practice, charts aren't very helpful. Theory is better. And this case is when our correlation coefficients are 0. Well, and for sure, what else? Remember that correlation coefficient, likewise average or standard deviation, itself a random number, because we calculate correlation coefficient on the basis of a random sample. And once this correlation coefficient a random number, we have to check whether this correlation coefficient is different from 0. Well, and how to check it? As usual, you should state null and alternative hypothesis, and here it is always the same. Correlation coefficient is 0, correlation coefficient isn't 0. And name of this parameter is rho. It is population correlation coefficient. Well, and next we calculate t statistics. We use our correlation coefficient and divide it by this. Well, and we apply n-2 degrees of freedom to find critical values, or we rely on p-value approach. And remember, if we need to calculate correlation coefficient and run the test, we should remember that our data must be continuous, highest interval or ratio level. And two variables are distributed as a bivariate normal distribution. So as two variables must follow the normal distribution. Boss. You cannot calculate correlation coefficient between qualitative variable and continuous variable. Instead, if you see that one variable is qualitative, for example, store location, and another variable is continuous, apply ANOVA, because ANOVA shows whether there is a relationship between qualitative and quantitative variable. Again, if you want to find a relationship between two continuous variables, calculate correlation coefficient. Once one of these variables isn't continuous, it is qualitative variable, apply ANOVA. And if two variables are qualitative, for example, so you should apply another test. We will learn it later. Well, no illustration of bivariate normal distribution is here. Well, so if we make a chart, we see that one variable follows normal distribution, another variable follows normal distribution, and hence both must follow the normal distribution. Looks like a mountain. What example of this test is similar to any t-test. So we have some distribution of our correlation coefficients. We should transform these correlation coefficients to t-values and check whether our estimated t-statistics exceeds its critical value. Well, conclusions about correlation coefficients. Always specify the population parameter of interest, formulate null and alternative hypothesis, level of significance, calculate everything, and reach a decision. So this is a theory. Now let's do an exercise in Stata. Well, clear. So part 2, correlations. Now, remove your dataset and let's open dataset from the status memory system use after. Please run this command to open dataset. Okay, well, our job here is simple. We need to find a correlation between two variables, weight and length. We have to find the correlation between these two variables. First step is to create a scatter plot. To create a scatter plot in Stata, you should type sc scatter plot. It is a short name of a scatter plot command, sc, and next you should list your variables you want to use, st, weight, length. Please create the same chart. Type plus if you are ready. Comment is here. Type plus if you are ready with that. Very good. Also, you can try to, so you know that in Excel, it is impossible to fit a trend line when you have such a chart. We can do the same in Stata. To do this, you should type these two symbols and use alpha and again the same variables. Weight and length. Type add these. So it's like a border, and L-fit means linear fit. And if you apply linear fit, you will linearly, you try to create something like a trend line in Excel. Okay, good. Next, let's estimate correlation coefficients. To estimate correlation coefficients in Stata, we have several commands. The first command is cor, or correlation. Well, let me show you this command help. Correlation, so doesn't, no, more than correlate. Yeah. So, correlate is a set of two commands, correlate, cor or pw cor. We often use pw cor and rarely use cor. Well, if you open manual, you can find formulas used to calculate them, and a lot of options as well. Here, by the way, you can find some examples Yeah. Well, how to calculate correlation coefficient? First, you can type cor, weight, and length. By the way, correlation coefficient is symmetric and the order doesn't make sense. And what we have, this is our output. This output shows total sample size, 74 observations, and look, we have 3 correlation coefficients. First two correlation coefficients are 1 because Stata estimates correlation coefficients between the same variables, weight and weight, length and length. It is 1 as expected. And it is 0.95, pretty close to 1 between weight and length. Well, do the same, please. Another command to calculate the same, to do the same, is to use PW core. Output is the same. Well, but what is important advantage of PW core? Because PW core can also estimate whether your correlation coefficient is statistically significant. To do this, you should use option SIG. SIG estimates p-values. Well, this is a p-value for this correlation coefficient. This p-value is smaller than any alpha, hence our correlation coefficient is statistically different from 0, as it is statistically significant. Please do the same and press plus if you are ready. PW core, weight, length, comma, SIG. Okay, very good. In addition to SIG, instead of SIG, we have an option star. Or no. Let me explain this maybe in more detail. Yeah, we have star option and print option. So, and level option sometimes, but not here. Well, this option has brackets. What we have to do when we work star, we have to calculate, we have to identify significance levels or alphas. What, for example, 0.1, 0.01 or 0.05. No, usually personally I use star 0.05. I do this, Stata automatically shows whether my correlation coefficient is statistically significant and 5% level. Look, I can change it. For instance, look at this. Could be. Well, do this. Do this, please. If you're ready, press plus. Well, and also you can add more variables here. For example, you can add price, you can add mileage. Well, all of these variables are continuous, and Stata will calculate correlation coefficients. And look, for example, here, some correlation coefficients are negative, some positive. Well, and this is an example of a correlation matrix. Well, and that's it about correlations. This is pretty simple exercise in Stata. But what is difficult when we work with correlations is interpretation. First, and I would like to spend maybe these 2 minutes on interpreting these coefficients. Please remember, we can use ANOVA and correlation coefficients to find relationships between two variables. For example, whether there is any relationship between level of education and income. Level of education is qualitative variable, income is continuous variable. We can apply ANOVA analysis. If we measure level of education using grades like high school diploma, college diploma, university diploma, PhD degree, so on. But if we measure education using continuous variable, how many years spent in educational institutions, and so income is a continuous variable as well, we can calculate correlation coefficients. But doesn't mean that education doesn't mean that more education is a reason why people earn more. Can we learn it from correlation analysis or ANOVA? No, we cannot. Please remember that correlation analysis and ANOVA always show us simple associations, simple relationships between two phenomena. So it is especially clear when we work correlation coefficients because it is symmetric and we can change the order of variables in our formula, and anyway it will be the same correlation coefficient. Hence it is unclear, so probably and it can be very difficult to state that so better education is a reason why people earn more. And this example is an illustration of the difference between association and causation. It is a pretty important concept in data analysis because when we conduct t-tests, when we conduct correlations, ANOVAs, in fact, we always identify associations. We cannot state that, for example, if you prefer self-employed, you will be so very rich. Well, because so we see that, okay, on average, so income of self-employed persons is higher than that of paid workers. But it doesn't mean that being a self-employed is a reason why people earn more. There are other factors we need to take into account in our analysis, and research design is also itself an important factor. Well, and the same can be said about correlations. So does it mean that, for example, if I find correlations between stock returns, for example, like return of Gazprom and return of so Rosneft, it doesn't mean that if Rosneft increases, if return of Rosneft increases, return of Gazprom will increase too, because Rosneft causes Gazprom. No, because again, it's just an association, and we can state the same, but vice versa. We can state that, so probably Gazprom causes the performance of Rosneft. Well, and you should always keep in mind this fact, and we, by the way, will check it in exam, that correlations, ANOVA, t-tests show us, in fact, associations, or they just compare averages, but we cannot use them usually to identify causal relationship. Why the causality is important for you as a manager? Imagine that you want to check whether, for example, whether holders of MBA degree are better workers. Well, you have, say, 100 employees, 30 employees have MBA degree, rest don't have, and for sure you can run t-test. Or if you have different MBAs, 1 year, 2 year MBA, you can run ANOVA probably. But what you can do with this analysis, you can just compare the performance. Is it higher, lower? But you cannot state that MBA is a reason why people work better. Why? Because always there are other factors we cannot take into account. For example, selection into MBA degree and non-MBA degree, or a decision to earn MBA isn't random itself, while people with certain characteristics prefer MBA. So usually they know English, or they have a good command of English, they have experience in a foreign company, or so they are entrepreneurs or former entrepreneurs. Well, so they have higher educational degree in a good university, and because of that they try to earn MBA degree. But definitely, and for sure, they have some abilities, talents which we cannot observe. And once we cannot take into account all of these factors, we cannot state that that MBA is the reason why people work better or worse. Uh, well, and unfortunately, our simple statistical tools we learned by this moment cannot do this. So, and we can try to do this if we conduct an experiment. For example, if you manager in a HR department, you can randomly choose people and send them to professional training program. And next, and after the completion, you can compare the performance of those who completed it and didn't complete it. Well, in this case, you can be closer to causal relationship. But anyway, there are better tools to identify more precise causal relationships, which are beyond our course and which you will learn in econometrics. But please, again, to sum up, remember that ANOVA t-tests are used to compare averages, while t-test 2 averages, ANOVA multiple averages. Well, correlations are used to find relationships mostly. No, ANOVA also can be used to find relationships. But all of these tools cannot give you causal relationship. They show you just associations at best. What will we do next? Next week, we will learn the analysis of qualitative variables, i.e. proportions, comparison of proportions, descriptive statistics for proportions, and if we have sufficient time, we will learn maybe some, and we should also learn chi-squared test. And I think that's it. So our lecture is over today. So thank you for your attendance. And if you have